Okay, in this moment, I regret that I missed my classes of Castellano. I was actually looking forward to my classes this year, but that is the tragic story of an academic professor. I noticed that the first 6 classes I couldn't attend, so I gave up the idea, but it would have been better. When I was preparing this presentation, I was very enthusiastic, and the screen disappears. That is probably to hide my mistake in the date, but I think that I was so enthusiastic that I changed the clock not by 1 hour but by 1 day. So it is today indeed 28 October. I decided to speak about something that I believe is complementary. I am just an ordinary professor at the university, so I cannot tell you about fantastic achievements on an industrial level. I was actually quite impressed by to see what is happening in Spain on desalination. That is amazing, and I think that this is a country that makes a lot of progress in that sense. So I'm in the right place. But what we can do as from the academic side is to give some suggestions. What can be done? What are the achievements that we see in the laboratory that could be something not today, but maybe tomorrow they could be applied on industrial level. So that's what I wanted to do. To illustrate what we are doing in research laboratories in the universities, this is what we did in the past. I like to show this because it shows how research was done at some time. This is an experiment by Nollet, in the time of Nollet, the person who started first with the observations of osmosis. So that is the founding father of membrane technology, and this is what they did. This is an experiment to measure conductivity of electricity in the laboratory. I can assure you that life in the laboratory is much less exciting than in those times today. And then if we go through the history, we always say that membranes are a young technology, but actually there has been already in the 19th century that people have built up the foundations of membrane technology, and you see a few of these familiar faces here that we all know, but the faces are a bit forgotten, apart from this man here, who was also one of the developers of the fundamentals of also membrane technology, much more than but also membrane technology. If we continue in the history, then there are some important milestones, and I will discuss here about the electro-driven membrane processes. And what is remarkable is that already in 1955 in the United States there was already large-scale electrodialysis operational. It is a bit forgotten now, because now we are more than half a century further, and electrodialysis, electro-driven membrane processes are still a little bit in the corner. Why? Because very soon they were overshadowed by this man here, Sidney Loop, who developed reverse osmosis in the 1960s. This was in the beginning was a crazy idea to use membranes at pressures of 100 bar to do desalination of water, and people were laughing away this idea. But later on this improved, and it took about 3 decades before reverse osmosis overtook the thermal desalination methods. And then of course electrodialysis was also a bit in the corner. And then now we are in a very exciting era of membrane technology. We see, on the one hand, we see the developments on a very large scale. Of course, desalination, reverse osmosis plants, and I think that from an academic point of view, that yeah, this is an established technology, so this has a proven performance, and as academics we are looking more like at other things. We are working on this kind of membranes, but this is not something I want to discuss today about improving membrane performances, fouling, etc. By looking at membrane synthesis and improved membranes. And it is, we can discuss a lot about that, because I think that in the membrane markets, especially reverse osmosis, there is there are not too many different products that you can buy. It's pretty much standard, and if you look at the materials that are used, yeah, you don't have too much choice. So I think that this is also an area where a lot can be done. But we see also that there is a lot of new developments that we should follow up, and that might be relevant as tomorrow's technologies. And I mentioned here forward osmosis, reverse electrodialysis, the use of bipolar membranes, which I will say something about today. And these are a few of the faces that I put up here, and they are not there by chance. I am involved in the European Membrane Society, so I try to look at who are the people that are dominant in membrane development today, and these are actually a few of our honorary members of the society, which have contributed a lot. There is here Heiner Stratmann, who worked on electromembrane processes, Enrico Drioli, Tony Fain, Roger Benheim, Marian Nystrom, and Yuri Ampolsky from Russia. Those are the people who will be the faces that should be remembered in the future, or at least that's what I believe. So I like to track this the foundations of membranes and where it comes from. One of our new honorary members is Karl Bödecker from Germany, and he wrote a fantastic paper about the origins of membrane science, where he develops how these ideas have grown in the 20th century, starting from a stupid idea in a research lab, but then ending up into the large-scale applications that we see today. So this is something we should follow from the origins and see what is happening in research laboratories. Now back to electromembrane processes. This is the graph that you would see in the comparison for desalination, where you see here the distillation. This is the cost of the desalination as a function of the salt concentration. Distillation is the old technology, it doesn't depend on the concentration, but it has a relatively high cost, and this doesn't change. This is the same cost as some decades ago, in fact, more or less. Whereas we see there also, well, ion exchange is clearly too expensive, but these two others here, this is reverse osmosis and this is electrodialysis. And this explains clearly why electromembrane processes are a bit overlooked, because the range where here where the electrodialysis would be less expensive than reverse osmosis is pretty narrow. Not too high concentrations, not too low concentrations, and those are concentrations that are probably not the most interesting. Something brackish from 1 to 8 grams per liter or so, more or less, which has some applications. But if you look around the world, this is a world map showing the concentrations of salts in different oceans and the seas. And of course there is a variation, and there are some places where electrodialysis would do well. There is the Baltic Sea has a low salt concentration that is almost brackish water, but the rest of the oceans has a larger salt concentration, and yeah, reverse osmosis always wins, and that's the reason why electrodialysis has remained a niche. Now the situation is changing. Electromembrane processes are quite old. They were suggested in the first time in already 1890, with patents taken in 1900, 1902. The first publication that I found that I can relate to electromembrane separations was 1903, more than 100 years ago, in German. And then the process development as we know it today is 1939. So that was pretty early. And this looked almost the same as electrodialysis that we know today, with 3-compartment approach, with a brine solution and a permeate and a diluate solution, like we do it also today. And not too much after, so it's repeated here, 1955, large-scale application, and this was one of the first. I like to show this from an academic point of view. It's a bit of self-criticism, in fact. Electrodialysis, academics would show you this kind of graphs to demonstrate that this is a very important technology. This is the number of academic publications as a function of time, and you can see that there is this exponential increase. So conclusion is that this is very important. But I was doubting a bit, and looking critically at the idea of making such graphs, I tried the same, and I looked at chemistry to see what is the trend for chemistry. And of course, chemistry is not something that changes too much. The interest in chemistry is the same as half a century ago. This is what I saw. It's on the left-hand scale, so the scale is very different, and we write much more publications on chemistry, of course, but the trend is exactly the same. And then I did a third test, and I looked at fruit flies. You know, fruit flies, those are these nasty insects that if the fruit is starting to be a bit rotten, that come to, and of course this is something insignificant. That is clear, but still you can do the same, and you can claim that fruit flies is an emerging technology. So this proves nothing at all. It's a bit of self-criticism towards the academic sector. We just publish too many publications, and this is proving nothing at all. And I think that we should rather look at the industrial translation and how these papers are actually applied in the field. And much of this work remains in laboratories and never comes out of those. Electrodialysis, why should we look at it today? Well, there are some counterindications. Electricity is needed for electro-driven membrane processes, and electricity is costly. So that's not very attractive. On the other hand, we have, with electrodialysis, we have a direct removal of ions instead of filtering by reverse osmosis. In reverse osmosis, the water goes through the membrane. In electrodialysis, the ions go through the membrane. So the more ions we have, the more costly it becomes, of course, because every ion has to be transported. And that's the reason why we have to look at this concentration range. In principle, these membranes are not selective. So traditionally, brackish water without any selectivity, that's the application that we can do, which gives a niche market and a static market. Not too many players because it's a small market until recently. This is now quite changing a lot, and today this is an emerging dynamic field with a lot of new applications, and this is what I want to explain you today. But first of all, I want to say something about this electricity issue. Starting from an investigation that we did in a total different area, using CO2 capture. We wanted to use sodium hydroxide to absorb CO2 and then to produce sodium carbonate crystals. Doesn't matter too much, but I wanted to look at the production of the sodium hydroxide using starting from a brine, using bipolar membranes, because here using electricity would also generate CO2, obviously. So I wanted to make the balance. Here we are taking CO2 out of flue gases, and here we are producing CO2. What are we actually doing? Is it positive or is it negative? I will skip this. This is the result. it depends on the way you generate the electricity. If you use an traditional source of energy, coal, heavy oil, fuel cells, natural gas, then the balance becomes negative. Then actually what we are doing is to generate more CO2 than we take from the flue gases. So that makes no sense at all. The conclusion is that we have to look here at the renewable part. If we use solar, wind energy, or hydroelectric energy, the picture changes, and then we have a very positive balance. This is for a specific application, but it can be taken as a test for sustainability, where the message is that if you really want to develop a sustainable process, then we should look into combination of electrodialysis with renewable energy. This is something we already see in applications, because it is attractive, especially using solar cells to have direct production of electricity and then combine it with desalination. To remind you of the process of electrodialysis, we have the feed solution and a stack of anion exchange membranes here with the plus and the cation exchange membranes. Anode and the cathode. The cations go to the cathode, they go through the cation exchange membranes, and here all the ions come together and are concentrated, and this generates a concentrated stream and a diluted stream with less cells. Looking at the market, this changes a lot. I did an investigation of which companies are active in electromembrane processes, whereas 10 years ago we would have just the first three. Fumatech was also there, but all these other suppliers are actually emerging in the market, and we see that, for example, in China we have. I have one, but I'm sure that there are at least 10 or 20 players. There is the Mega in Czech Republic, who has a lot of applications, and it's pretty immense. So this is something to be considered. I saw that in the afternoon there was a presentation on spacers, which is a very important point, and I just want to emphasize this in electrodialysis as well as in other processes. It is a somewhat overlooked issue. Spacers in electrodialysis look like this, and they determine the energy performance of the system. If you have a high velocity through your stack, then there is a pressure drop, and that's the energy penalty you have to pay. If you have a low velocity, then you have problems with concentration polarization. You have to optimize this, and it's the spacers who can help you with creating turbulence in the system, so that you can have the best performance of your stack. Spacers are pretty much standard, so I think that in spacer development there is a lot of room to improve this. There are some ideas on that. There is this idea of creating a tortuous path in which the spacer is folded back, so that you change the pathway and then operate at lower pressure drop. Also interesting, and I will come back to that later, is this idea here to have integrated spacers. What people try to do is to in the casting of the polymer to insert the material of the spacer, so that you create a sort of expulsion here. If the polymer dries, you can remove the spacer again, and you have something like this, a membrane with an expulsion that acts like the spacer material, and this would allow to operate systems without a spacer. Still an early development, but it is clear that here there is a lot of benefits to be made. Well, electrodes is just for completeness to be mentioned. I think that there everything works fine. if as long as you use a good electrode that is inert, and we have to remember that we have oxidation at the anode side and reduction at the cathode side, which generates chlorine gas or hydrogen, which requires specific precautions. But that is a detail that I think is under control. The operation, this is a picture that was taken from Novoselp in the Czech Republic. You can see here the installations. They made these stacks in series. They make many of those in standard conditions, which allows to operate at larger scale. What you can do is in one of these stages there is a desalination of well, they claim 55 to 60% possible, but it's designed to have 40 to 50% of desalination within one stage, ranging from 50 to 99% in an overall stack. And applications would go anywhere from 100 milligrams per liter to 12 grams per liter, so that's extending the range already quite a bit. This is still a classical application, still normal desalination units. But there is more today, and I believe that this is in three areas. The first is the membrane materials, new membrane materials that are developing, and of course every company tries to have their own brand and their own new development, which generates a lot of creativity in membranes. Bipolar membranes are one of these things. It's still not too much on the market, but there is a lot of applications that can be done if we have more of these bipolar membranes. I will explain this. Secondly, separation efficiency. So far I've been talking only about non-selective removal for sticking to the brackish water application, but if we have some selectivity in the membranes, that could change. And then thirdly, this application and industrial opportunities that are also emerging. First of all, these selective membranes, it's something that we focus a lot on in research. And this would allow to do much more. This shows an anion selectivity with sulfates and chlorides, and this first membrane SA is a non-selective membrane, whereas the second membrane is a selective membrane. It has some selectivity between sulfates and chlorides. So what would happen is that we have a product stream that has mostly the sulfates, and a brine that has all the rest, mostly the chlorides. So this is what would happen. The sulfates end up in the product. Yeah, this is an academic example because chlorides and sulfates, okay, its applications are not too many, but we can do this with other monovalent and multivalent ions as well. And what we are mostly aiming at is phosphates. And if we have a stream with that contains phosphates, in this way we can produce a concentrated stream of phosphates that can be then recycled, and phosphates are a valuable product that could have an economical value when you recycle it in large quantities in the right way. And there is more of this. Something we tried here is nitrate selectivity. It's maybe a bit futuristic, but I'm a very enthusiastic person, so I try. Nitrates and chlorides. And nitrates are chemically exactly the same as chlorides. They have the same charge, they have the same size, the same charge density. So to separate these from one another, that is very difficult. Still, nitrates are something we don't want for many reasons, whereas chlorides are in most cases are well, not so important. So we did this by making polymers with specific affinities. We can obtain separation factors not too high, but we were pretty happy with these values of up to selectivities of 2. Similarly, for cation selectivity, selectivity between calcium and magnesium and sodium. Yeah, seawater for desalination, and we target the sodium. But maybe we can also target other cations from seawater that have an added value. And there is a lot of interest in this. We are looking at magnesium for reasons that is related to phosphate recovery, because we need magnesium to produce struvite as a phosphate-containing mineral. A cheap source could be seawater, but there is other things in seawater that you could valorize. I was last week in China, where they try to develop such membranes for lithium selectivity to generate lithium from seawater. If you have a selective membrane that is selective enough in an environment of a lot of sodium, this can be done. The bipolar membranes are a specific type of membranes. A bipolar membrane is a combination of an anion exchanger and a cation exchanger with positive charge, negative charge. What happens then is that if you immerse these membranes in water, there is a water layer in between, and if you have electricity from between the electrodes, then there will be an effect of electrolysis between the membranes, generating H plus and OH minus, which goes in opposite directions. Very powerful tool, because you create a pH difference on both sides of the membrane. And pH is such a powerful weapon for an engineer that you can think of many applications, and I will give some examples of that. The easiest is the application to brines, which I believe is a direct industrial application for brine solutions. This is something in Belgium we are facing with. We have a lot of brine streams that are generated by companies that are not necessarily near the sea, companies that are inland. They have evaporation processes in whatever way, and these brines are a problem. Traditionally, nothing is to be done about that, and the most advanced technology is mixing it with the rest of the wastewater so that you don't notice it in the wastewater treatment plant. But you can use this with bipolar membranes to produce difference in pH, to produce acids and base. If you have a bipolar membrane, then you can create with this difference, you can split the salt into the acid and base. That is a chemical wet dream. With these bipolar membranes, you can do that, and it's not even such a difficult application. There are some challenges related to that, and the concentration is a very important point. For industrial viability, you have to be able to produce something more than 2 molar for the acid and the base. There are some challenges related to back diffusion, related to scaling of membranes, and this is something we are working on. If you concentrate a stream, then you can expect in a brine that there will be some components that will be super saturated, so that you can have these components as scaling on the membranes. This is an issue that is to be considered case by case, but we have the solutions for that. Large scale applications, I like to give this application as an example. A typical example, it comes from China. It's a colleague in China who is doing this on a large scale. It's a wastewater stream from the production of glyphosate. Glyphosate is a herbicide used all over the world as the herbicide. In Europe, I think everywhere you go, if you go to the garden shop, then if you buy a herbicide, it would be something like this. This is glyphosate. It's a nasty molecule because it's small, difficult to remove, and it is produced with a lot of salts. In the production, there is the wastewater contains this glyphosate, something you don't want to discharge in an acid environment. So very difficult to treat. You have to remove these salts, and it can be done by using these bipolar membranes. So what you do is simply to remove the salts as an acid and a base. The diluate contains only the organic compound, which can be directly recycled, and you eventually produce 3 streams: acid, base, and glyphosate. So it's a perfect example of a closed loop by using electricity. I already mentioned this phosphate idea. It's we call that that idea, the Electrodialysis, because we make selection between different ions, and instead of sulfates, then we try this with phosphates. And the example that I showed was directly applicable to phosphates, but it depends on the pH. And the phosphates are one of these typical compounds where the geochemistry is determined by the pH. So if we operate at the right pH, here at pH 9, we have the same situation as sulfates, and we can generate this concentrated phosphate stream. This is an example of this where you can see in the product stream, this is the concentration of phosphates, this is the sulfates, of course the same charge, so the same trend, and this is the nitrates and the chlorides. You can see that in the this is just a preliminary experiment as a function of time, so we stopped the experiment here, but as a function of time we can see the split. The multivalent ions go up, the monovalent ions go down. So this is something that that is directly applicable. We also looked at the configurations, how the stack is made up, and we can start to play with this. This order of membranes can be easily changed, and we studied some examples. This is an example of production of chemical where we had the bromide compounds that we have to exchange for an OH minus. So we can do that by applying by using the OH minus produced by the bipolar membrane. It's not a very difficult application, but we were faced here with the issue of product quality through these membranes, and we started to develop this idea of playing with the stack. As engineers, you don't have to stick to this idea that was proposed in 1939 of a 3-compartment stack, and we started to add membranes. Here there is an additional cation exchange membrane to prevent the leaking of compounds, in this case the bromide, to have a better product purity. We were worried about the electricity consumption, and this is what we describe here. Here are two curves. Well, it's actually two different current densities, so we have to compare the green ones and the red ones, which is exactly the same curve, the same energy consumption. The additional membrane didn't increase the energy consumption in the stack, whereas the purity, the level of impurities is from here to here. This is the 3-compartment stack, and this is with the additional membrane, is much lower. So this proves that you can actually play around with this. And then we did a lot of these experiments. Another application with a compound that we produced, where we had the problem of this is a simple stack with only one anion exchange membrane. This produces concentrated sulfuric acid. Problem is that H+ is one of these ions that can sneak through an anion exchange membrane. It's a very small ion, so it may diffuse back to this compartment and pollute our product compartment. Well, with what we know, it was pretty easy to solve, because we can simply add another membrane to that, which doesn't improve it doesn't increase the energy consumption, but improves the product quality. So playing around with these bipolar membranes, we can do a lot. This is an application that I found described, an easy application which tries to generate CO2 from seawater. Another compounds that you can take from seawater by using the geochemistry of the carbonates. You can convert everything to CO2 in an acid environment and then easily extract the CO2. Novel applications. Just very briefly, this fuel cells. If we talk about electromembrane processes, the fuel cells come up. And you can see it as a proof of what is fuel cells. There was a hype 10 years ago about fuel cells, but today you don't hear too much about it anymore. Yeah, that is true. A fuel cell uses hydrogen or methanol to produce the H+ and to have the electrons in the electrical circuit. So what you need is a cation exchange membrane to bring to transport the H plus. So this is indeed, yeah, I don't see a fast development. This is not related to the membrane. The membrane that is used there is usually the naphthalene membrane. It's a membrane that has been on the market for half a century, but the challenges are rather different in the development of a hydrogen economy. Service life is a problem. The supply of the fuel is a problem. So you can buy these cars made of with a fuel cell, but you would have to pay 2 times or 3 times the price of another car. So this is the reason why it's not coming through, and it's rather something not technical. But where I see a lot of development is in bio applications, in the combination with bioreactors. You can do well, and especially if you produce something that has an added value. You use electricity, so you should do more than just desalination. You have to produce something from the water that you are treating. And there is a lot of potential. If you look at phosphorus, in this case, there was a sludge was treated with heavy metals and phosphorus. Interesting, but you have to look at some alternative configurations. What you see is that in this stack, like this classical stack that I've shown, this would not work, because this would foul and block the membranes immediately. So you have to think of systems that have a non-classical design, like this. You have to combine the membranes with reactor technology, and this is what actually is already existing in membrane bioreactors. This is the same principle. We probably should extend that more to have more applications. And in fermentations, in fermentation reactions, there is it's very typical to have a compound that is limiting the reaction. In excess of sodium, in this case, this is for citric acid production, would hinder the reaction. This is an easy application for electromembrane processes. Removing the sodium would enhance the reaction. The same is for other productions to produce hydrogen gas in an anaerobic bioreactor. You have the same effects. You produce other compounds, the acetic acid, formic acids, and citric acids, which are limiting the reaction. If you remove those, you can do much more in your reaction. But again, in another configuration probably. And this is something that where we have to think of more from an engineering point of view. And the same goes for the microbial fuel cells. This idea of the fuel cells that I showed you is, yeah, we can probably change that by using water that contains organic matter, wastewater, probably enriched wastewater with a lot of organics. Microbes are in this reaction to produce the H+, instead of using the methanol. The rest is exactly the same. Using a proton exchange membrane, and you can directly produce electricity from wastewater. Is this something good? Well, the idea is certainly good, and the membranes are doing an excellent job. The problem here is that the system in itself is still pretty expensive, and this is in part related to the membranes themselves. Membranes are not cheap in such an application if you consider wastewater or cheap sources. But there is an interesting development that I noticed, and it was actually the first time I saw in the literature this kind of membrane. This is a 3D printed membrane used for an electromembrane process, a dense membrane, and I have to say the performance was not so good. The membrane that was produced was quite thick, and the power density that could be obtained. These are classical membranes, and this is the membrane produced with 3D printing, so it's 10 times lower. Still, this is something to be followed, because this would allow to produce membranes on a massive scale. If you can print the membranes, the cost of the membranes would be immensely much lower. If you do that at least on a sufficient scale. So I think that this could make applications like the microbial fuel cells possible. These are the first ideas, the first results that come from this, but I think that this can be extended to other technologies, and of course 3D printing has its limitations in terms of which polymers, in terms of what you cannot make porous membranes, for example, with 3D printing technology. But why not a reverse osmosis membrane, for example? There is a lot of applications in the food industry, and this is also a very exciting area where many of the ideas that were already there years ago now become possible. Peptides are those typical compounds where depending on the pH you have charge or no charge, positive and negative charges, and if you play with the configuration of the membranes, then you can easily separate different proteins from one another. And this is something in the food industry that has thousands of applications. There was a difficulty because there is one specific amino acid arginine in this. So this had this binds very strongly to the membranes, and for that reason poisoned the membranes. It reduces the ion exchange capacity, and the membranes become not functional anymore. Today this is changing, and people have been exploring other kinds of membranes, and especially the use of ultrafiltration membranes is a trend there. Charged ultrafiltration membranes can do just as well as dense membranes, and in fact using proteins which are a bit more bulky than ions, this can give excellent separation properties without this effect of poisoning of arginine. So I think that in biorefinery applications anything is possible today. It's just a matter of developing the right applications. Other food applications that you can find in the food industry, this is directly applicable. It's in fact the origin of electromembrane processes back in 1898, started from food applications. So there is a lot of need to tune ion concentrations, and if you can cope with the properties of the solutions, like for example the fouling effect or the viscosity of the solutions, this is something that the membranes can easily do. A lot of examples in juices, and I looked up a few of these, but I stopped because you can replace pineapple juice by apple juice, orange juice, cranberry juice, and all these different kind of juices have more or less the same trend. I have to say something about reverse electrodialysis, because it's also in academic environments it is a hype to think of reverse electrodialysis as a way of producing energy. So it's a different way of looking at seawater and river water. If you have the mixing of the two, the mixing energy can be produced in the opposite way to produce energy. So instead of using the energy as the input, the energy becomes the output. Is that viable? Well, you can write very nice publications about that. That is for sure. But in terms of industrial application, I have some doubts there. There is both a technical issue and there is a fundamental issue. The fundamental issue is related to the use of water. And we were talking about using water as a resource. Reverse electrodialysis is sacrificing water resources to produce energy. I don't think that there is too much application to do that for real. Rivers that contain water of good quality are probably have to be used as first used in water production. And, if you think of, for example, the Colorado River in the United States, a fantastic river, but when it flows into the Pacific Ocean, it's just there is not too much water left. So using that water for energy production is probably not too beneficial. Also, I'm almost done. the flow of the river is also an issue. We measured this the potential in Belgium, but actually, if the flow is not large enough, then the salinity gradient goes a lot inland, and you can find the salinity kilometers up to the river in land inwards. So there is not a real point where you can actually use this mixing energy. That is a fundamental issue, but there is also a technical issue that needs to be solved, and that is related to this pressure drop, the spacers. If you apply electromembrane process for desalination, then you have to pay the penalty for the energy. If you want to produce energy, then that goes off your results, and if the result is minus the energy that you have to sacrifice is negative, you cannot do anything. And this is the case at this point. The pressure drop is just too large. So what people try is to look at these spacers and to see if we can solve this by improving the spacers, spacers with less pressure drop. So coming back to this idea of profiled membranes and different kinds of membranes where you introduce the spacer into the membrane material itself might be a solution, but I don't think that this is the evolution, or this is the industrial application that we are waiting for tomorrow. Some conclusions. I've touched many points, but I think that I hope that I convinced you that ion exchange membranes are today emerging from classical applications to selective configurations, selective membranes with a special emphasis on bipolar membranes, which can have the benefit of changing the pH. I believe that the bioreactor applications are very interesting, and we can do a lot when combining with the bioreactor if we can combine the process with the production of something that we can recycle from a stream, whether it's wastewater or seawater. Food applications are emerging, while reverse electrodialysis is probably an interesting idea, but not something that I see as an application for the coming 10 years or so. And that is where I would like to conclude. I think I will just in time.